This is not full screen. Okay, can you see anything here? Something?
It's not a full screen, but we see the presentation. So let's proceed.
You will start in such a form.
Let me start. First of all, I would like to thank the organizing committee and especially Professor Vladimir Petrov for kind invitation to visit this seminar and report my submission results related to quantum mechanics.
Would you please speak louder, because we don't hear you very distinctly.
I will try. Okay, my report is devoted to solution of the Schrödinger equation. And this approach.
Excuse me, Mikhail. Sorry, your voice is too faint. Could you speak closer to the microphone? Before your voice is much better.
You know, my microphone is remote and this is from computer. Can you hear right now or anything else? Can you hear me now?
Well, it's not easy to hear you.
Okay, you can read just from screen. Okay, my work is devoted to solution of the Schrödinger equation. The wave equation, quantum mechanics, and general solution and the place space are obtained. This is a short introduction, and here I just do you hear anything here at this time? No. Can you hear me?
It's very hard to hear you.
It's very hard to understand what you say.
Just speak louder or closer to the microphone.
I will try. What about now? Can you hear me better or not?
Now it is better, yes.
It's better, okay.
Please continue like this.
Here just remind some basics from quantum mechanics. Especially Schrödinger wave equation in quantum mechanics is usually solved in terms of special functions or numerically. The general approach to solve the Schrödinger equation is to reduce it to the equation for the hypergeometric function or some special function. To do that, one needs to do first, okay, you can read yourself. We use here the abbreviation SV as SW, which means Schrödinger wave function, known as a psi function. Here are some relations, you see, right here, which can be used to derive, just to make definition for de Broglie. Louis de Broglie wave suggested in 1924. Here is just lambda B definition, and here is for massive particles. Now we can consider quantization of the de Broglie wave. Consider the same mnemonic quantization using the de Broglie wave. We use, as I mentioned above, and noted in many authors, that the de Broglie wave, double lambda B, is standing wave. This is important. This is standing wave. If so, then we may have resonant frequencies corresponding to the wavelength equals to lambda this. Half of lambda B, lambda R denote the resonance frequency. Thus, we can write the generalized expression can be written as equation 3. Or in another form like this, equation 4. Lambda R, this is lambda, another definition. Let's compare 4 with the Heisenberg uncertainty principle, equation 3. Inequality 5. This is that a minimal value of 4 is the value h bar over 2 at n equal to 0. Thus, 4 can be considered as equation 4 can be considered as a decoding of the Heisenberg uncertainty principle if you put lambda r equals delta, like this we show here. And the standing waves can be described by the periodic functions cosine and sine, like this shown here. One-dimensional Schrödinger equation. This one. This equation has general solution as superposition of two plane waves. Equation 7. Here, C1 and C2 are in general complex constants. However, there is another approach to solve the Schrödinger wave equation. It's known that this equation can be derived with the help of the Bohr's correspondence principle. This fundamental principle has been used as a stage of creation of quantum theory. It's used to establish correspondence with the classical functions and operators of quantum mechanics. Okay, this is well-known state. Moreover, the correspondence principle points out the way to the simple solution of the Schrödinger equation. Okay, this is enough for correspondence principle. We transform 6, this equation, Schrödinger equation, which is the energy eigenvalue problem, to the equivalent form, equation 8, which is the problem on eigenvalue problem for square. This gives the solution, gives the equation in the phase space. E2. The general solution of the equation in the phase space is given by equation 8. Here phi is kx, w here is the classical action. Now, the question is interaction. Quantum theory is used the concept of action in quantum mechanics. In semiclassical approximation, the action in quantum mechanics is used in the terms of the expansion of the in terms of Planck's constant h bar, like here. But in the quantization condition, the classical action S0 is used and corrections S1, S2, and so on have no physical meaning, but lead to artificial problems such as divergence of the solution at the turning point. In our approach, the concept of action in quantum mechanics is not necessary for the theory. Let us show that the Schrödinger equation and its solution can be obtained from the classical action. In the general case of an X-ray particle, we consider the conservative system which, when the Hamiltonian h equals to shown here, is not an explicit function of time and equals to the total energy. Only in the case when Hamiltonian is not explicit function of time, h equals to energy E, which is a constant of motion. In this case, the Hamiltonian principal function has the form 11, where Wx is Hamilton's characteristic function. The Schrödinger equation in this case we write in the form for this operator, and seek the solution of this equation resembling the plane wave as closely as possible in this form. Here is classical action. And we don't use, remind again, we don't use action in quantum mechanics, just classical action. The first derivative of this function with respect to a variable x gives this equation. Here, px is derivative of w the x, derivative from the reduced classical action. The second derivative gives this equation 15. Look, The right-hand side is complex expression. And it's p square plus this one, this term. Where p square is the value, it's generalized momentum squared. The complex equality 15 gives the Schrödinger equation 12, this equation, only in case if this condition is met. I mean this term equals to 0. The complex equality. What does it mean? The iterators in quantum mechanics are Hermitian. Items, their eigenvalues are real. The squared momentum operator p squared in the left side of 15 is Hermitian if the condition 16 is met. The Planck's constant is constant one, not 0. Hence, the derivative p prime x equals to 0. This means that the generalized momentum at px can only take discrete constant values p per p. The condition 16 is the key. Q1 in solving the Schrödinger equation and supplies the hermiticity of the squared momentum operator in 15. We emphasize that only if the condition 16 is satisfied, it is possible to obtain from 15 the Schrödinger equation 12. Equation 12. This is the equation. Functions in mathematics can take both continuous and discrete values for specific values of argument. The requirement of 16 is a prerequisite for the permitted movements in quantum mechanics. It determines allowed motions or stationary states as of a quantum system. Items, the generalized momentum px can only take some constant discrete values, momentum eigenvalues p bar. Let me remind that to solve the equations of motion in mechanics, it may be necessary to take into account some constraints that limit the motion of the system. For example, the beads of the abacus are constrained to 1D motion by the supporting wires. Constraints may be classified in various ways. If constraints can be expressed in as equation connecting the coordinates of particles and possibly time, in the form, this one, then constraints are said to be holonomic. Constraints not expressible in this equation are called non-holonomic. Typically, such constraints depend on the particle velocities or momenta, like this equation, and possibly the coordinates. The key is that this is the key point in our approach. We treat 16 this constraint as a non-holonomic constraint. It restricts the moment of particle so that the momentum is constant. I would like to remind that according to Noether's theorem, there are 3 integrals of motion for conservative systems. This is energy conservation, momentum conservation, and angular momentum conservation. So here we just demonstrate that for closed system, not only energy, but also momentum are constant of motion. That's why this is a key moment also, because this results in a very simple solution of the Schrödinger equation. Solution of the one-dimensional Schrödinger equation. Thus, equality 16 leads to from 15, shown above, to the equation 12, and is general solution of the form, like for the plane wave. Here, p is phase variable, dimensionless phase variable, defined as this integral. The Schrödinger equation 12 can be rewritten in the Sturm-Liouville canonical form, equation 18. Where the notation here? Transform 18 to the dimensional space variable c equals to double x This can be done using the identity equation, identity 19. That gives the equation of the form 20, where psi equals to square root from t psi. The function or functional delta t here is given by equation 21, where epsilon is given by this form, and has meaning of the potential in the phase space with the properties, the following properties. Here, this we consider the function delta as it has specific properties.
Mikhail, you have five minutes.
Yes, we have delta t equals 0. Okay, this function behaves like potential, in the phase space. Now, the roots of this equation, this is the details, you can see. Now, the corresponding eigen equation for in the phase in this region below from 12, from 20 to this equation. I name equation 1, Schrödinger equation in the phase space. Now, we can transform this equation to the couple of equations given by the system, where we see that two equations. In fact, we consider two equations instead of one Schrödinger equation, we consider system two equations given by interface. The general solution of these equations are given by this system. This is a physical region, classical region, and non-classical region. Solution of this equation. Okay, now I construct connection formulas using this general equation. General solution to this equation. Then we have the system through this kind of system 25, which yields this relation connection with between constants. The most popular and important, the most important popular in the position as a two-dimensional connection. Okay, from this connection formulas, I derive this condensation condition, which coincide with W, the condensation condition with the quasi-classical condition. But this condensation condition is exact, not exactly the final solution for tutoring problems can be written in the form of standing wave. This is state function, which is defined for x. This x1 and x2 are Turing points. Exponential decaying solution, and here is the oscillating solution in classical region. Phases are defined like this. Here is non-relation condition. We define as usually from this equation. Now, here is the oscillating part of this solution. 28. The oscillating part of the solution has a form of standing wave. The form is given by, okay, the argument is given by this Kn, this eigenvalue, plus bound space. And here is the phase. Okay, now shortly, the three-dimensional problem. In this case, we are seeking for a solution in this form. Where W is in case of separable variable, WR is given by this. Here is the equation. Now, as above, for one-dimensional case, we just consider number acting on psi. We have this one. The second derivative we use Schrödinger equation and requirement for constraint consider the above. Thus, from this, we derive the in case of separable variables, we obtain the following three equations: 34, 35, and 36. Radial for variable theta and variable phi. Now, we have obtained the corresponding quasi-classical equation of the form, where delta x is a canonical operator. Note, it's what you know that canonical operator does not contain derivatives. because only this requirement for one-dimensional problems to correctly apply WKB method is just to reduce original equation to the form of canonical form without Phys derivatives. Only in this case, we obtain the correct energy eigenvalues for all known solvable problems in quantum mechanics, not unsolvable. All this couple of examples I will give below, but all these applications and other problems have been considered in my earlier works. Here is canonical operator. Now, let me show you some examples.
We don't see your summarize.
Summarize, okay. In summary, I would say just my presentation, I can summarize this result as follows. Solution of the Schrödinger equation can be obtained in terms of elementary functions. To do that for three-dimensional problems, we need to separate if variables are separable. They can reduce original equation to one-dimensional equations which can be solved by the method presented above. So, and to do that, we don't need to use so-called action in quantum mechanics. We use only classical actions which enter into arguments of exponential functions in general condition. And we don't need, and the general solution is given by the form, equation 17, where Phi is expressed, where is dimensionless phase variable given by. So after that, using just simple calculations, we come to the equation 15 for this form, and applying this kind of constraint or restriction, we treat this condition or constraint as a non-holonomic constraint for momentum P, which for physical solutions for eigen should be constant value, and this is just a low value in the solution of any kind of problem. For free motion, this is obvious, but in case of bound states, in case of the potential, especially for bound for two-dimensional problems, this results in the exact energy eigenvalues for all known problems in quantum mechanics. Here are just examples from this.
I'm sorry. I think you should summarize your talk because we have no time. The time is over. Now please give main conclusions and.
Okay. Main conclusion like this.
Okay, thank you.
This conclusion can be just found in my previous work because the conclusion is that solution can be Schrödinger equation, solution of Schrödinger equation can be obtained from elementary functions, in terms of standing waves. You can find the references of sites in many publications, and we can find a lot of examples. I just solved all problems in quantum mechanics, and also unsolvable problems in quantum mechanics using this approach. This is my method of solution. I would call this method as asymptotic solution of the Schrödinger equation, and I generalize this method not only for I apply this method only for Turing problems, but also for any Turing problems, and references can be found in this work, in my references. And I have found that, for example, kernel potential generates a complex eigenvalues. But this, I would like to show, there is no time now, and I would like to show my results published in previous works, where I solved this problem for 3 and 4 Turing problems and so on. So this method and asymptotic approach.
Okay, I am sorry, but we have to, I think, to stop now.
Okay.
Thank you for your presentation. Fortunately, we have no time for
Okay.
questions.
Okay. I'm sorry for inconvenience.
And we have to stop and
Okay, understood. Okay,
now
thank you very
we
much.
break for lunch. Thank you once again.
Thanks.